No.
You ever seen the bowling ball on the string bit? You hold it up to your nose and you let go and the bowling ball goes down and then comes back? Yeah, that in essence, the only way that is not dangerous is if it doesn't gain any energy. So it can only come back as far at most as far as it started, unless you throw something else into it. So if I push the ball, then yes, that's dangerous. But if you just let go, it can only come back up to at most here.
Is it a coincidence that the distance the coil went was about the same, just a little higher?
Just coincidence, yeah. Because if I had changed the spring constant, this would have been a very different number.
So, if the spring constant, or is it possible to get a really small number, like a really small decimal?
Oh, for the spring constant? Yeah, it is. I mean, I'm trying to recall off the previous lab. Slinkies are generally in the single digit. So if you just had a really weak spring.
Do we have to measure the springs
The spring constant?
Yeah, do we have to measure that?
We will at some point. I'm just introducing the springs right now. We will get into springs in more detail later on.
Okay.
At which point it'll become very clear about how to find the spring constant.
Wait, so is there friction in this ball or not?
No.
Okay.
Are we going to add friction?
Sorry, what was?
Are we going to add friction?
Are we going to average?
Add friction to this?
Maybe.
Okay.
There are some interesting problems without it. All right, questions to hear before we do the problem which involves a quadratic. If you get into the mattress business, this kind of thing makes a difference.
I have a question.
Yes.
So say we drop this ball on the spring. If it's an ideal spring, or just in general with springs, would it always bounce back up, or would it just stay compressed if the object was too heavy?
In an ideal situation, the ball would bounce back up to that height. Because there's energy's not being lost, so whatever kinetic would be turned into potential, then back to kinetic, and then back into the gravitational potential it started with. It would go on forever.
So it just bounce up and down?
Yep. All right. What are the forces that will be acting on the ball
Just wait.
to start with, and then,
Then the spring constant going back up?
or the spring force? Yeah. So I have only conservative forces involved here, therefore,
Potential energy.
it's looking for something more general, grand sweeping, and incredibly important in physics.
Gravity.
If only conservative forces are involved, why are they called conservative?
They don't lose energy, or You said non-conservative?
No, only conservative,
Yeah,
and you're on the right track. Say it
they,
again.
they don't lose energy, so it would just go forever.
Yes. What I was hoping for was energy is conserved.
Oh.
But yes, it doesn't lose energy. Energy initial equals energy final. This is going to start out exactly like the other one did. I got kinetic initial plus potential initial. I've got only one type of kinetic here. I've got two types of potential. And then it comes down to the formulas. And then the same thing final. What's the formula for kinetic energy?
1/2 mv squared.
That was a little less enthusiastic than the last time. The formula for gravitational potential energy, where little g is relatively constant.
mgh.
And the elastic or spring potential,
K equals 1/2.
got it already.
1/2 K delta X.
And just the same stuff, but final. I guess let's give it a spring constant. Let's give it the same spring constant. All right, we got 6 terms there. Three initial, 3 final energies. What can we get rid of?
Initial speed would be 0. Initial speed would be 0.
All right. And what's the clue that the inertial speed is 0?
Something is holding the ball before it drops.
The key word there is dropping, as opposed to throwing. All right, so initial V speed is 0. All right, what else?
Final speed is 0.
Yep.
And then the initial spring force would also be 0 because nothing's pressing on it.
Let's work on the wording. Yeah, the initial spring force would be 0, but not really energy here
It's at equilibrium.
at equilibrium. Your thinking was spot on, it was just wording.
And then do we do something like we did last time with the height that we set to 0?
Yeah, it's gonna be a little bit tricky here because delta x is gonna be from here.
Mm-hmm.
That's your delta x. And but we don't know what the final height is. And it doesn't, so where do you pick h is equal to 0? Depends upon where you want to put the math. So we can make h is equal to 0 here. This is also a logical spot, and then however far it compresses has some merit as well. You will get the same answer whichever one you pick.
I think we should do where it starts.
Here?
We'll do, yeah.
I agree.
All right. So look, it has no energy. It's apparent. So. Any parents in the room? All right, just to save on, so I don't have to keep writing stuff. This delta x here, I'm just gonna give it the letter y. So I have 0 equals mg something plus 1/2 ky squared. What's the final height?
The same thing, 0.
You set the initial height to 0.
Yeah, but if we bounce all the way down and it's conservative so we don't lose any energy, we go all the way back up and then we just stop there.
We're only,
Except the question is how far will it compress?
Yeah.
And you're sort of skipping out the whole compression part.
oh yeah. We don't know the final height. We need to find the final height.
Yeah, but we need to, in terms of what we have over there, what would the final height be?
I think 0 meters. I'm getting there's the compression, and are we stopping when it's fully compressed?
Yeah,
Ah,
that,
so it'd be whatever, how far it compresses plus, or base, yeah, plus 3 meters.
okay. Very close. There's one small little thing you missed. All right, so it starts here, it's gonna go down to here. So I know this is 3 meters plus y, so this is 3 plus y. That's how far it's gonna compress, which is what you just said. But I'm not gonna put 3 plus y in here and just start working it out. Why?
Because you can't. Can you not? When we're saying y, it's still the same y as the delta x.
Yep.
Okay.
I don't know if it's just this because we chose 0 at the top.
Therefore,
It would have to be negative.
yes. Negative 3 plus y. We've defined y so that y should be a positive number, and so we have to acknowledge that somehow. Well, we'd still have a negative in there. So, distributing out, we now have, the mass was, let's just go ahead and, that's 50 right there. And that's 20 right there. So negative 150 minus 50y plus 10y squared.
And we're assuming Earth 2?
Yeah.
Yes.
Okay.
Now we have the quadratic. I have some students who leave it in this form. Personally, that just seems disturbing to me. But we all have, of course, the chocolate stars. All right, I can divide by 10. That makes it convenient. So I get y squared minus 5y minus 15 equals 0. And no, it's not going to be an easy factor. All right, so y is equal to 5 plus or minus the square root of 25 minus 4 times 1 times negative 15 divided by 2 times 1. So I get 5 plus or minus the square root of, let's see, that's 85 over 2. That's 9 point something. We will have 2 answers, and I want, one of these answers will make sense for the problem, but I want us to sort of discuss what the other answer means physically.
So I got 9.2195. no, that's just the square root of 85.
Oh, 9.2195, okay.
Okay, I got for one of my answers, I got 7.109. And for the other answer, at 2.109.
Units?
Meters.
Meters.
All right. So which is the correct answer?
The -2.
Why?
Because in our problem, we're going down, so we would have to take the -1.
How did we define y?
So why? Did we say positive?
We define y as going in that direction, so it's the positive answer, that's the right one.
Wait a minute, did we say down's positive?
We didn't establish. Why? You wondering why?
Yeah, I'm wondering why y is positive
I define y to be positive in that direction.
okay,
This is how much it compressed.
okay.
So then, do we take the 7 and the -3? Or is it just 10.1? If we take the positive? side?
Just the positive, so 7.109 meters is how far it will compress.
Yes. Plus the 3.
Oh.
So would we get 4 or would we get 10?
It would be, the ball falls 10 meters, but the question is how much does the spring compress? The spring could compress that amount.
The 7.1.
Yeah, the ball is going to fall 10.1 meters.
Okay.
What does the negative answer mean though?
Okay.
I'll just assume that it expands.
Okay, keep going.
Well, since it's expanding, but it's going on the opposite direction,
Yeah, okay.
right? So that's all I can go for.
Okay, you are so close. Remember, we're finding energy conservation, we're finding places where the energy is constant. So we have a certain amount of energy to start with, we have the exact same amount of energy at that maximum compression, and then there's another bit of energy up here at 2.109 meters above where we started. If the ball actually hit the spring and stuck to it, it would get to maximum compression, that wouldn't change. But then as it goes up, the ball's not gonna come off of the spring, the ball's gonna stay stuck to the spring, and the spring's gonna stretch.
Very top.
And it's gonna stretch 2.109 meters if the ball's still attached to it,
So,
from
Just-
equilibrium.
yeah, so it's just when the ball, I guess, is just about to leave the spring? When it's going?
The ball's just about to leave the spring at this point right here,
Mm-hmm.
because that's when the spring will start to slow down, but the ball will slow down too, but the spring will slow down faster. Sorry, I lost the question, try it again.
So it's just when the ball is just about to leave or when it just left the spring, like contact with the spring?
Oh, that
Yeah.
-2?
Yeah.
No, the ball is, so the ball hits, compresses, comes back up, if it stays stuck to the spring,
Mhm.
then the ball's gonna reach this point and the spring is still
Down.
attached to it, and that's 2.109 meters.
Okay.
And so the ball's, part of the premise here is the ball's not leaving the spring. Questions?
The -2 is like -2 from the original state of the spring, not after the.
Correct.
compression, right?
It is, y is defined from the initial state of the spring. All right. Got one more energy thing to do. We haven't done black holes yet, right? Any questions before I erase?
we had a bad spring, like it just wasn't as strong as it once was, would it just go, like it wouldn't go as high?
No, actually it would. If it's a weaker spring, it would compress more.
Okay.
And then, because once you pass the equilibrium point, you've got weight acting down and the spring acting down,
Mm-hmm.
the spring force acting down. If it's a weaker spring, then, assuming it's stuck as it comes up, the spring's not going to be exerting as much force downwards, and so it won't go as high as the initial height, but it will go higher than that. The stiffer the spring, the harder it is to stretch it. So weaker spring, it'll stretch more. Anything else? Planet X. I am going to launch something from the surface. How we launch it is completely irrelevant. All I know is that when at the surface, when it's being launched, it is at its maximum speed. Vmax. If something gets launched, gets shot up into the air, from our personal experience, it will come back down. The faster it is initially, the farther it will go up in the air. Hopefully it's not a shock. If it is, after you've bought your slinky, you buy a ball and throw it up into the air. The question is, how fast does this need to be so that it never comes back? Because as soon as it leaves, as soon as it's launched, it's in the air, got the force due to gravity acting on it, it's moving this way, force due to gravity that way, it will be slowing down instantly. But if it's going fast enough, well, it will never slow down enough in order to completely come back. This is an